Hello, welcome to our tutorial on training XNOR networks for EFLX's embedded FPGAs. This tutorial will cover an overview of an XNOR network, and then we will go through an XNOR architecture example for EFLX embedded FPGAs. Then we'll train an XNOR network using Python Jupyter Notebook. We will then extract the binary weights from the training and then add the trained weights to an XNOR network RTL and then synthesize the RTL, compile the synthesized RTL with EFLX compiler, and lastly we will summarize. Convolutional neural networks can be broken down into three types. Standard convolution, where the images are inputted as real numeric values, integer or floating point. Weights are also trained as real numeric values, integer or floating point. This type of convolutional network uses multipliers and adders as operators and takes the most amount of computational and memory resources. Then we have binary weight convolution, where the images are inputted as real numeric values, weights are trained as binary values. This type of convolutional network uses adders as operators and takes less memory and computational resources than standard convolution. Then we have XNOR convolution, where the images are inputted as binary values. Weights are also trained as binary values. This type of convolutional network uses XNORs and bit counters as operators and takes the least amount of memory and computational resources. We will be using the XNOR network. The XNOR network requires no max, does not require much memory resource, and can fit into a small embedded FPGA. This type of network is good for small AI on the edge application. This is an example of a fully connected XNOR network. The input is a 28 by 28-bit binary image. The weights are 28 by 28-bit binary times 10 for 10 classifiers. Each image is XNORed with a weight classifier to give us 784 bits. These 784 bits go to a pop counter where the ones are counted. The pop counter outputs are accumulated for each classifier. The classifier that has the most ones is the selected classifier for that image. An XNOR operation is comprised of XNORs and a bit counter called pop count. The way that it works is shown in the two matrices in the bottom. The X matrix is 0, 1, 1, 1, for example. The W matrix is 1, 1, 1, 1. The dot product of these two matrices is 3. The XNOR of these matrices show that there are 3 ones. Combined with pop count, the XNOR operation is performing the dot product of the binary matrices. We are using a small pipeline XNOR architecture for embedded FPGAs in this tutorial. The block diagram above, this architecture does an XNOR of every 28-bit row of the image with 28-bit row of weights for 28 rows to form a 784-bit XNOR. The image row is selected by cycle. This is repeated 10 times, selected by index, each time selecting a different 28-bit by 28-bit of weight. Once all 10 rows have been XNORed, the classifier determines which index has the most ones. The block diagram below shows the implementation of this architecture. We have an image RAM and a weight ROM. The weight ROM is 7,840 bits. The image RAM is 784 bits. We have a cycle counter and an index counter. The cycle counter selects the row of the image as well as the row of the weight. The index counter selects the different weights. The image and weights are XNORed 28 bits by 28 bits at a time. The pop counter counts the ones per XNOR operation. The pop counts are accumulated and classifier determines which class the image falls in. We will use a Fashion MNIST dataset to train our XNOR network. The dataset has 10,000 images, 28 by 28 bits grayscale, and 10 labels. The labels are numbered 0 to 9 and correspond to the following labels: 0 being t-shirt or top, 1 trouser, 2 pullover, 3 dress, coats, sandal, shirt, sneakers, bag, and 9 being ankle boot. You can see the image representation of each of these categories on the right. We will now train our XNOR network using Jupyter Notebook. Jupyter Notebook allows us to interactively run Python scripts. So first, we will import all the TensorFlow dependencies and read the MNIST dataset. When the MNIST dataset is read, we start the training for our fully connected XNOR network. For our training, we define the shape of the tensors first, the image tensor as 784 bits. We define the shape of the weight tensor as 784 bits also. The weights are converted to binary using the binarize weight function. The convolution is defined by the yconv function. Then we create the training ops, the cross entropy, the training step, prediction, and accuracy. Then lastly, we define the training loop. We choose the epoch of 1. We only run the training loop once. We choose a batch size of 50, so we update the parameters after 50 images are sampled. And we train 10,000 images. Then we train the network by running the training script, and you'll see that the accuracy starts at 0.09 and the steps start at 0 and continue, steps increasing, accuracy increasing. We'd like to get an accuracy in the 0.8% or 0.8 or 80%. We'll continue to train until we see that it's at 99 or 10,000 steps, the accuracy around 70%. Then we'll save the weights into a pickle file. We'll save the weights and images, the images in both int16 and binary, and the weights in int16 and binary. Then we'll simulate our model to see what the prediction looks like. We will simulate the network using the saved weights to see if we can detect all 10 patterns. We can see that we did not predict all 10, only 6 of the 10 patterns. We will have to retrain the network to generate new weights and see if we can get all 10 patterns predicted. After several trainings, we were able to get weights that were able to predict all 10 images. I saved these train weights to a file. Then I resimulated the network with these 10 weights. In the simulation, you could see that all patterns were predicted correctly with these trained weights. Next, we save the binary weights. We select all the binary weights and copy them to a text file. Once the weights are copied to a text file, we reformat them so that they can be used by the network that we described earlier in a ROM readable format in RTL. We copy the reformatted weights to the ROM in the Verilog file of the XNOR network. Then we synthesize the network with the retrained weights and generate an EDIF file to be used by the EFLX compiler. We compile the network that we synthesize using the EFLX T40 compiler. The compiler shows that the network only takes 426 LUTs and can easily fit into a EFLX 1K tile. In summary, XNOR networks can be used for simple image recognition. You could also train the network with different datasets such as MNIST handwritten characters and different image sizes as well, not only 28 by 28. Also, XNOR networks fit in small embedded FPGAs and are applicable for inferencing on the edge. For more information, please visit our website at flexlogics.com. Thank you.